Hello everyone. I am Anuj Kumar. I am a PMR of TA for this course, Coordination Chemistry, and I am here to discuss the assignment 6 of this particular course, right? This session is basically related to Jahn-Taylor effect and spin crossover phenomena, right? So, I will be discussing some basic problems related to these terms, okay? I will be trying to get some responses from your side also, okay? So as usual, I will be showing two problems first, and I'll wait for your answers, and thereafter I will explain the same. Okay. So these are the first two problems of today's session. So you have to identify which transition is responsible for the coloration of the complex. Following the practice, what you have to do first, you have to determine the oxidation state of central metal atom. Okay, so basically it is titanium plus 3. Okay, and what will be the electronic configuration? It will be 3d1, right? So it, since it is a octahedral complex, so if I fill the electron like this, okay, so what will be the transitions? So this electron can shift to this level, that is T2Z to easy level, right? So what will be the color? If let's say if there is an energy difference between T2Z and EZ, and if I write the expression, that is this one, so you can get the corresponding lambda of that color. Okay, so these transitions will be responsible for the coloration of this complex. Okay, so this transition is responsible for the coloration of titanium echo complex, right? And the second one, what do you mean by strong field ligand? Okay, so waiting for your answer, and after that I'll explain. If you know the answer, just put in the chat box because it is a basic questions related to your theory part, right? There are four statements. Ligand causes low crystal field splitting. Ligand causes lower splitting between d orbitals, and ligand favors unpairing of electrons, or it forms high spin complex with transition metal ions. So basically, if I talk about some octahedral complex, okay, you will be getting the splitting like this, right? So in case of a strong field ligand, this energy gap is very high. Okay, so I was telling that. Okay, so I was discussing if there is a strong field ligand, the energy gap between these splitted orbitals is very high. So what basically the strong field ligand does, it just favors the pairing of electrons. Okay, so this statement is incorrect, right? So if you are getting a pairing of electrons, you will be having a low spin complex, right? So this option will also be incorrect, right? And ligand cause low crystal field splitting. No, it causes the high crystal field splitting because the energy gap is very high. So the second one will be the correct one, and in this one it will be T2Z2 EG. So here is the explanations for both the questions. So as I have explained, the central metal ion is present within plus 3 oxidation state, and the corresponding electronic configuration is d1. So the electron has the possibility that it can basically go under transition from T2Z to EZ level. So that is the reason for its coloration, because there is some certain amount of energy difference between these two orbitals, and this energy difference will be corresponding to any specific wavelength, that is lambda, right? Moving to the second one, ligands that cause large splitting of d orbitals and favor pairing of electrons are called strong field ligands, right? Okay, so moving to the next two, in jet out situation, the octahedral complexes, the higher energy state. Basically, the question is asking about which orbital will be the higher in energy when it is a case of jet out situation. Okay, so if you are having any octahedral complex like this, and is basically this bond is basically elongated, that is Z out situation. So what will be the higher energy state in this case? Okay, in case of normal octahedral, what you will get, right? Dxy, dyz, and dzx, and these two orbitals is dx square minus y square and dz square. So if you are having this one as a long bond, that basically means that the electronic repulsion between this interelectronic repulsion is very low. So that means this orbital is stabilized, right? The ligand having, the orbital having Z contribution will be getting stabilized, right? So you can choose the correct one. And the second one, the magnitude of this crystal field splitting depends upon, these are the factors, the geometry of the ligands, right? It is correct whether it is a strong ligand or it is a weak ligand. So the magnitude of delta will depend upon, and the oxidation state, yes, and nature of ligands is also, right? So geometry, whether it is a inner orbital complex or it is a outer orbital complex, right? So all of these are the suitable options. Okay, so here is the explanation. In this case of the Z out situation, the energy of d orbital with Z factor are lowered. Okay, so since the bond along the Z axis are elongated, this is the most preferred distortion and occurs in most cases, right? So in question it is asking the higher energy state. So higher energy, that will be this one, dx square minus y square. Clear? And these the crystal field stabilization energy depends upon all the factors given in the question. Okay, so the next two, what will be the crystal field stabilization energy of high spin d4 system? Just calculate it by your own, right? And tell me the answer. I'm waiting for you. Next question is related to the theory only. What do you mean by the John Taylor effect? It is type of geometrical distortion. It is observed among octahedral complexes. It reduces the symmetry and energy of the nonlinear molecular system, right? So if you know the answer, please type in the chat box. Anyone? So no issue. So this is a high spin d4 system, right? So if I fill the electrons, right, it will be 4. Because it is a high spin system, no electron will be paired up, right? So just calculate the total energy. So let's say if it is a berry center, okay, and it will be zero point 0.4 delta naught, it will be zero point 0.6. So just count the electrons and multiply, right? So it will be minus 3 into minus zero point 0.4 delta naught plus zero point 0.6 del naught, right? So it will be minus 1.2 del naught plus zero point 0.6 del naught, or it will be zero point 0.6 del naught. Since there is a no pairing of electrons, so pairing energy will be 0, right? So I can write it minus 3 by 5 del naught. So this will be the right answer. And in second one, all of these are basically related to the John Taylor effect. So here is the explanation, right? So the John Taylor effect is a geometrical distortion of non-linear molecule systems that reduces its symmetry and energy, right? So basically, what the effect does, it provides the stability to the complex. Okay, so this distortion is typically observed among octahedral complexes when the two axial bonds can be shorter or longer than those of the equatorial bonds, as you observe in the typical octahedral complexes. Some Z out Z in situation, elongation, compression, right? So if Z out situation, the ligand lying on the this Z direction will be moving forward. That's why this bond will be elongated and rest the bonds are compressed. And John Taylor effect is basically due to the unsymmetrical distribution of electron in the easy level. So whenever you have a group of complexes and you have to identify which will show the John Taylor effect, just you have to fill the electrons in T2Z and EZ level uh, basis on the ligands given in the complex. And if you are getting any unsymmetrical distribution of electrons in EZ level, you will be getting a strong John Taylor effect, right? So the first one is asking about the same. Which one of the given system exhibit strong John Taylor distortion? So just fill out the electrons in the respective orbitals, and you will getting the information automatically. And the second one, what do you mean by SCO? SCO basically the spin crossover, right? So it is a phenomena where the spin states are changed by an external stimulus, right? So it is a reason where the complexes are present only in high spin state. No, they can exist in both low spin and high spin states, right? So it is a reason where only the low spin complexes. So these two options are incorrect. So this one is the correct answer. So just try for the first one, please. Try to solve. Just fill out the electrons. Okay. So the low spin D2 system, that means the electrons are paired up, and high spin means electrons are uh, filled first one by one. Okay, if I fill this one D9 system, since it is a high spin system, so the electron filling will be like this, right? And low spin D3 system will be right. Sorry, it will be high spin, and low spin will be uh, this one, right? So here there is no filling of electrons in easy level. Same goes for the D2 system, right? So it can also exhibit the weak John Taylor distortion. But in case of D9 system, you are getting a unsymmetrical filling of easy orbital, right? So in that case, you will be having a system with strong John Taylor distortion, right? So here, these unfilled electrons are symmetric. You cannot say these are unsymmetric orbitals. Okay, so the second one will be the right one. So here is the explanation. In octahedral complexes, John Taylor effect is most pronounced when an odd number of electrons occupy the easy doubly degenerate orbitals. These situations arises in complexes with the configuration D9, low spin D7, etc. Okay, so here both high spin and low spin D3 systems has this configuration, so they cannot show the John Taylor effect, right? Low spin D2 system exhibit weak John Taylor distortions, right? So I have already explained the same thing. The next one was related to the definition of spin crossover. Okay, in theory classes you have studied this SEO in detail. Okay, so this is a phenomena that occurs in some metal complexes wherein the spin state of the complexes changes due to an external stimulus, whether it is some pressure or some temperature, right? The stimuli can include temperature or pressure. Spin crossover is sometimes referred to as spin transition or spin equilibrium behavior, right? So I think the solutions are clear to you. Yeah. So the next one, you have to identify which technique can be used to detect the SCU, spin crossover, right? Many techniques are there that can be used to detect this spin crossover system. Okay, just you have to identify. And in the second one, just define what is low spin complexes. Okay, so here are the three conditions you are given. In this case, delta O equal to P, right? This one and this one. So what will be the correct relations? Yeah, so I'm getting the answer. First is A. Okay. So why Raman spectroscopy cannot be used to detect the spin crossover systems? In classes, it has been already explained, right? Most pair spectroscopy is also related to the uh, metal center study, right? You can identify which oxidation state the metal is exhibiting. And magnetic susceptibility measurement, which is basically done by the Gauss balance. Okay, so I think all the techniques can be used. Okay, and what about the second one? Low spin complexes are having a high value of crystal field energy. Okay, and less pairing energy, right? So moving to the explanation part. So many techniques are available to detect this phenomena. It can be magnetic susceptibility measurement, it can be XRD, right? X-ray diffraction, okay, mouse pair it can be, and it can be also the Raman spectroscopy, because the spin system or the arrangement of electrons, right, can changing the can change the behavior of complexes or can change the vibrating behavior, right? So X-ray structure detects this by measuring the bond distances between the metal ion and ligands, and Raman spectroscopy is used to identify the spin state, which is very predominant. Okay, whether you are having a high spin or low spin, in both the cases, the spin state will be different. Okay, so if you calculate the spin multiplicity or you calculate just the total spin, that will be different. Okay, because in strong field ligands, some electrons will be pair up and their spin will be cancelled out by each other, right? So these all techniques can be used. The other one, complex can be classified as high spin or low spin depending on the crystal field splitting energy and the pairing energy, right? So when the crystal field splitting energy is greater than the pairing energy, that will be called a low spin complexes. Or if you are having a reverse case, that will be a high spin complex, right? So electrons tend to fall in the lowest possible energy state, and since the pairing energy is lower than the crystal field stabilization energy, it is more energetically favorable for the electrons to pair up and completely fill up the low energy orbitals, right? So what will be the right one? This. Okay. So this question is basically related to the splitting of orbitals in this square anti-prismatic geometry, right? So what is the most stable state, or you can say which orbital will be having the low energy in case of square anti-prismatic geometry? Okay, in earlier classes you have already uh, studied about different geometries. Okay, from drawing that geometry you will be getting the basic idea about the inter-electronic repulsion of the ligands, right? So on the basis of that repulsion, you can just draw the crystal field splitting, or the splitting of orbitals. Okay, so I will be explaining in next slide. And the second one is the relation between octahedral and tetrahedral crystal field stabilization energy, so splitting energy, right? So always this delta octahedral is greater than delta t, and the relation is this one. So you can write it this. Okay, right? So if you are having any square planar complexes, it will be higher than octahedral. Okay, so this is basically I have drawn the orbital configuration for different geometry ranging from linear to octahedral, right? So in case of linear, you will be having a higher z square orbital, right? Okay, and in octahedral, you already know these will be triply degenerate, and these are the easy level. Okay, so you can easily draw this orbital by seeing the structure. Okay, right? If I compare this square pyramidal and octahedral complex, you can see here one bond is less than octahedral. Okay, so what you can observe there is the interelectronic repulsion or uh, on the z axis is less as compared to this one. So here you can observe this dz square orbital is getting stabilized. Okay, and if I talk about the trigonal bipyramidal geometry and consider it these three ligand in xy plane, okay, and consider it as z axis. So here the same situation arises. The repulsion on z orbital is great, so that will be higher in energy. Okay, and in the square planar complexes, right? So both let me draw like this. You can see there is no orbital on z axis. So z dz square orbital will be getting more stabilized. Okay, and in case of tetrahedral complex, just splitting is reverse to the octahedral. Okay, so here you are getting e and t2, right? So moving to the pentagonal bipyramidal, this will be the splitting. And if I am having a square anti-prismatic structure, right, and a trigonal prismatic structure, so you can just remember, right? So although pentagonal bipyramidal splitting is mostly nearly the same, but what you have to do, you have to just exchange these orbitals. Okay, so these two will be the higher in energy and these two will be the lower, right? And in case of trigonal prismatic, okay, this dz square will be lower and xz and yz will be higher in energy. So basically, if I draw the trigonal prismatic structure, it will be looking like a prism. Okay, so consider here is a metal and this is the z orbital. So you can see the three ligands are very close to each other. Okay, but in case of this square anti-prismatic, let me draw it. It will be like this. sorry, this one. Okay. uh, so if I consider here this Z orbital. Okay, so these four ligands are far apart from each other. So here the repulsion will be less. So that's why this dz square will be lower in energy. So the question was asking that what is the most stable, right? That means which orbital will be least in energy. So that will be the dz square, right? Hope it is clear to you. So there are three tetrahedral complexes you are given. You have to determine the order of the tetrahedral crystal field splitting energy, right? And here you have to calculate the crystal field stabilization energy. Okay, for this is also a tetrahedral complex. Just solve and tell me the answer. Here you have to just compare which will be the strong ligand and which will be the weak ligand, and you will be getting an idea which complex will exhibit the large splitting. Okay, so if you remember the spectrochemical series, right, I think the order will be like this. Okay, so this ligand, or you can say NCS, this ligand will be the strongest one, right? And thereafter this one and this one. Okay, so what will be the order? C will be highest in energy. Thereafter, it will be A and then B. So this will be the order. Okay. So in the next one, just write the oxidation state. What it will be? It will be plus 2. Okay. So it will be 3d7. Right. So since it is a tetrahedral molecule, it will be T2 and E. Right. Just fill the electrons. Right. So what will be 4.6 plus 3 into zero point 0.4 del naught. So it will be minus 2.4 del naught plus 1.2 del naught, right? So it will be minus something like 1 point del naught. So del naught equal to 10 dq. So it will be 12 dq, right? Clear? So moving to the next two, which of the following statement is incorrect? The strong field complexes have this delta O greater than P. Weak field complexes have less than P. And high value of pairing energy implies difficulty of pairing of electron, or pairing of energy of weak field complexes is less than the this value. Okay. or you can also write at this. Okay, so if delta now is larger, it will be a strong field complex, right? So this will be the incorrect one. So Gauss balance can directly measure the gram magnetic susceptibility, magnetic moment, or Bohr magneton value, diamagnetic corrections. Okay. So for calculation of magnetic moment, you can easily use VSM, vibrating sample magnetometer. But Gauss balance just measure the gram magnetic susceptibility. That is this one. Okay. This Gauss balance is already discussed in classes, right? So the next one, if a metal forms two complexes in the same oxidation state, in one complex the magnetic moment is 4.9 Bohr magneton, and in another it is 0, right? So the information is, in another state it is diamagnetic, in one state it is paramagnetic. So which will be the fit metal for this description? Okay. So, what are the electronic configurations for these four? Okay, so starting from the this one, it will be 3D3. Okay, it will be 3D7, right? It will be 3D6. Okay, it will be 3D8, right? So, what will be the right answer? Okay, just calculate the situations in both the cases, whether it is high spin or low spin. Okay, so if I fill, considering is at a as a octahedral complex. Okay, so 3D3, it will be a high spin complex, and one is unpaired. Okay, clear? And if I talk about this one, 3D6, right? It is a high spin complex, and sorry, okay. So the unpaired electrons are here 4, and here 3. Okay, and right. If I pair up, it will be like this. So unpaired electron is 0, right? So basically, the formula for magnetic moment calculation, it is this one, n into n plus 2. Okay, so if you are having a 0 unpaired electron, you will be having a magnetic moment of 0, and if you are having unpaired electron 4, that will be under root 24, and you will be getting value something like 4.89 or 4.9, you can say. So this metal is just fitting this description, right? Try for the remaining three. Okay, check whether uh, these metals or any one among these metal is also fitting this description. Okay, waiting for your answer. Anybody is trying to solve? If yeah, please tell me. In case of first one, if I talk about the low spin complex, the unpaired electron will be 1. So you will be getting under root 3, that will around 1.73 more magnetron, right? And in case of the second one, that is 3d7. Okay, so 7 electrons can never be paired up. There is at least one electron unpaired. So the second conditions will be not fit. And the next one, that is 3d8. Okay, so it can be dimagnetic, but if I fill, okay, so the unpaired electron here is 2. Okay, so what you will be getting, root 8, something around 2.7, right? So the first condition will not be hold. So the third option is appropriate, right? So the next question is the correct order for octahedral splitting energy for these complexes. Okay, so just you can easily compare. First of all, this cyanide ligand is strongest, so it will be causing the large splitting energy. Okay, so you can just cut down these two options. Okay, just think about these two. Okay, and tell me which will be the right one. Okay, this is also a D7 configuration. It is also it is D6, right? It is also a D5 configuration. Okay, and the water molecule is weak ligand. So you are in all three cases you are having a high spin complex value, right? So just since it is a octahedral complex, these three, all the four are octahedral. Just fill the electrons, right? I'm taking the case of D7. Okay, if it is a D7 configuration, right? This is barycenter. Okay, this will be minus zero point 0.4, this will be zero point 0.6. Okay, so just multiply by 5.4 plus this 2 and plus these are the just pairing energy and calculate by the number of pairs, right? So similarly you can calculate for d7, d6, d5 and just compare these values. Okay, I'm telling you what will be the right strategy for comparing these. If you, in some case, if you are having a 2p, okay, and in one case you are having a P. Just multiply this one by 2. Okay, the pairing energy will be equal. Rest, the first term, that will be in terms of delta knot, you can easily compare, right? So the right option will be the second one you will be getting. Okay, so thank you. This was all about the assignment 6. This is done from my side. Okay, anybody is having any query, just type to the chat box. I think yeah, I'm not getting any response from your side, so I'm leaving the call now. Thank you very much for attending.